Here we're going to work some more examples using the fundamental theorem of calculus to evaluate definite integrals. So here's an integral. When we look at this integrand, this is not one of my, it's not in my list of integrals that I know how to do. So I have that long list of basic integrals that I know how to do. And so what I have to do is either go all the way back to the definition, which won't work, or try to use some sort of manipulation to turn it into one that I know how to do. In this case, the most obvious manipulation would be to try to factor and simplify. So remember, I bring everything along. Don't just put equal and start doing the algebra. You can go do the algebra off to the side, but don't call it equal if you're going to do it. But this is equal to, if I factor the top, I can cancel those out. So these functions aren't the exact same functions, but what I'm canceling out is not going to make a difference on this interval 0 to 1. If it did, then I would have a 0 in the denominator, and I probably couldn't apply the theorem anyway. But once I cancel it, I get it to this. And then we know that with definite integrals, with indefinite integrals, we're allowed to transfer the integral to each piece and evaluate, find the antiderivative of each piece. Well, since I'm finding an antiderivative, I can do that here. I can just find the antiderivative of x, which is x to the 1 plus 1, divided by 1 plus 1, that is x squared, over 2. And then the antiderivative of 1 is x. So there's the antiderivative, and I incorporate my notation so that I can say it's still equal. And then I'm done. I just plug in the 1, 1/2 minus 1. I subtract, and I plug in the 0. 0 over 2 minus 0. And so I end up with minus 1/2 when you simplify. So factoring, clearing fractions, working with trig functions, whatever we need to do, that's what if it's not in our list, then we've got to go through some sort of manipulation to turn it into our list. So this is not in our list. I want to evaluate this integral, but what I'm looking at here, I don't recognize it as something in our list. The most obvious thing to do in this one is to separate that fraction, the numerator, separate it over the common denominator of x. I can always push that back together because it has a common denominator, but I broke it apart because I now have 1 over e, 2 over x, plus 1. And so I know 1's in my list, 2 over x is not, but 1 over x is. And we know if I want to, in my mind, I can think of it this way. This is 1 over e, 2 over x, plus 1 to e of 1. And sometimes they don't even put the 1. Sometimes they'll write this one as just 1 to e dx. I mean, the 1 disappears. We always do that with math. But anyway, I'm going to leave it there. And so then what I would do with this one is I'll bring the 2 out in front. Now I can clearly see 1 over x is, that's something in our list. Now you don't have to go through all these steps. You could do it from here. But just to make it clear where that's coming from in case you didn't see it. So now I can do this integral. That's going to be 2. And this will be natural log absolute value of x from 1 to e. Plus, when I integrate 1, I get x. Evaluated 1 to e, and then I plug these in. So it'll be 2 natural log of e minus natural log of 1. And on this one, I get e minus 1, plugging those 2 in. And if I simplify, don't need the absolute value because e is positive, but natural log of e is simply 1, and natural log of 1 is 0. And then over here I get an e minus 1 still. So if I combine these and simplify, I'm going to have 2 plus e minus 1. So altogether I'm going to have e plus 1 because it's 2 and a minus 1. So this will equal e plus 1 or 1 plus e, however you want to write it. So that's what this integral of this function, that's what the value is on that interval 1 to e. Okay, here's another one. I'm going to try to evaluate 2 to the 2x. Now we do have this formula that if I have a to the x, the antiderivative formula is that this is a to the x. All our exponential functions give us the exponential function back, except when it's not e, you have to remember to divide by natural log of a, and then plus a constant in general. But I don't quite have that. I have 2 to the 2x. So I have to use properties of exponents to remember that this is, you can multiply exponents. When you multiply exponents, you can think of it as your base raised to a power raised to a second power. And you can put either one of these as the second power. Well, it's more convenient in this case to put the x as the second power, because that turns it into 4 to the x. So this integral becomes 0 to 1, 4 to the x. And now I can use this integration formula to give me that this will be 4 to the x over natural log 4. And that's evaluated from 0 to 1, which is going to be, plug in the 1, you get 4 to the 1. I'll just leave it for now. Natural log 4. 4 to the 0 over natural log 4. And about all I can do there is this is 4. This is 4 to 0 is 1. So I'm going to have 4 minus 1. They both have this common denominator of natural log of 4. I was going to pull it out. I could have pulled it out to begin with, but I didn't. So anyway, you end up with 3 over natural log 4. All right, one more. Cosine squared, very close to things that are in the list. We know that the integral of cosine is sine plus a constant. But that doesn't mean I can just put a squared here and a squared here and be done. That doesn't work that way. Those integral formulas, these indefinite integral formulas are very specific. It has to be exactly this, and I get exactly that. So what I'll do is change it using the an identity from trig for cosine squared. Cosine squared is 1/2 1 plus cosine 2x. And the reason that works nice is because we do know that I could actually, this is written a little more generally in the list of integrals, indefinite integrals. This is 1 over a sine ax. So that one we gave as one of our formulas. So I have cosine ax, in this case 2x. So here's what I have: 1/2 0 to pi. I took the 1/2 out in front. And inside I got 1 plus cosine 2x. And now I can apply the integral formulas to this one. I get x here. I get 1 over 2 sine 2x using the formula. And then I evaluate that from 0 to pi. So I get 1/2. Plugging in pi, I get pi plus 1/2 sine 2 pi. Then I'll subtract and plug in 0. Well, that gives me 0 plus 1/2 sine 2 times 0. And just to wrap this up, we can see that that's going to give me 1/2. I'll still have pi. Sine of 2 pi, that's 0. Minus, well, that 0 is gone, and sine of 0 is 0. So if you want to leave the parentheses for the time being. Anyway, so you can see all the calculations. I end up with pi over 2. So cosine squared, this is the area, because cosine squared is obviously positive, but on that interval, cosine squared has an area underneath it of pi over 2. So that shows you how sometimes we have to work to get an antiderivative. If we don't quite have just direct formulas like we had with derivatives, where you figure out which function you're trying to take the derivative of and you apply the right formula. Here you have to manipulate it sometimes, and that's actually why the rest of the course gets, or the rest of finding, the process of finding integrals, definite integrals, is a little more tricky than doing derivatives, because it turns out we have procedures and manipulations to try to evaluate integrals, whereas with derivatives, typically we just have formulas.